All right, great. Well, yeah, so I'm Alex. I am the GIS and Geospatial Data Coordinator at University of Texas at Austin Libraries, and I have been the 2025 chair of this group, which has been a great honor and privilege. So, um, yeah, today I wanted to pose this question, certainly not answer it, and maybe have a discussion in the context of kind of how do we align GIS resources from a kind of library uh, viewpoint in the age of AI and big data in GIS. And I'm specifically going to use satellite imagery, remote sensing as an example because that's what I've been working on in terms of building out some of our resources recently. And it's also where my research background is based in. And there was some really kind of what I think significant changes as I have been working with geospatial data that is satellite imagery based. So I start off with this in part because I think it's kind of fun to show a GIF in a presentation like this. But really, it's to illustrate a point in that this in 2017 took me about a day and a half probably to produce. So this is showing uh, NDVI images, which, if you're unfamiliar, uh, show like vegetation activity. So like productive vegetation, that's going to be the more light green, and then red is less active vegetation. And so this is imagery throughout a year in the Kalahari region in southern Africa. And then those dots are uh, GPS data associated with zebras, so like GPS collars on zebras. So it's showing zebra movement with vegetation. But the main takeaway here is that, yeah, in 2017, when I was really starting off as like a remote sensing practitioner, this was quite a labor, downloading individual imagery, working on it, storing it locally, things like that. At the same time, this new platform for remote sensing was proliferating, which is Google Earth Engine. So that engine part's important. It's quite different than Google Earth in that it's both a very large database worth of mainly satellite imagery data that's all stored on the Google Cloud system. And then it's also a platform for working with that data all on the Google Cloud system. And so what that has allowed is it takes away that kind of laborious task of accessing single images, downloading them, storing them locally, and basically puts this incredible power to work with endless amounts of satellite imagery in the hands of practitioners. Whereas, so now, like I produce this GIF of a continent within like 5 minutes. And so that this is the same type of data. This is NDVI showing vegetation productivity for a year. And yeah, just really easy to write like a few lines of like JavaScript code and produce this. So that's to say, like, there's really been a fundamental change in how remote sensing is done and how easy it is now to produce these kind of large extent products quite quickly and efficiently. And it's really brought in a whole kind of genre of these global extent studies where you can bring in high spatial resolution data, meaning that it's pretty detailed when you can think of like you can get down to analyzing like at the city block level, but then extrapolate that across the whole extent of the Earth because of this kind of cloud computing system. So this change in technology, it results in this change in the science and even the type of questions and type of research that can be produced. And so here's one example that I really like to point to and talk about, which is this high resolution global maps of 21st century forest change. And this is a really highly cited study, and like the results have been in a whole bunch of different models and all kinds of things that documents forest dynamics across the globe. And with that kind of power and a global study like this, there are lots of benefits, but there are also some drawbacks. One is that it's really hard to include local context in something like this. So there's a lot of controversy involved with a product like this. That is, I think still kind of being worked out within the remote sensing community. And now looking forward, and this is what relates to my map background that I talked about, I think is maybe something that signifies another pretty important change in how remote sensing is done. And that's these sort of AI-enabled synthetic images that we're now just seeing kind of come out for public use. So this is Google's what they have developed from all this data that they've been hosting on their cloud, which is what they call Alpha Earth. And it's really not a single image, and it's not an image at all. It's this like kind of AI model that pulls together all kinds of different data to produce what they kind of term as like a land cover fingerprint, where you can really effectively like observe change and different dynamics that you're looking at. So that's all to say that this is a very, very powerful product, but there's a lot of complexity that underlies it, and kind of like a whole genre of research that imbues that product. And so with this sort of really fast changing technology that shakes things up, that's where I'm really kind of questioning. So what resources do students and researchers need as they're now able to access these extremely powerful products with the ability to make claims about a whole Earth-wide phenomenon and things like that. And so that's really an open question, I think, for everyone, and I think goes beyond even GIS to sort of librarianship and to higher education in general. Is how are we providing resources and services to work with stuff like this, especially when like something like this could show up in an answer to someone typing into a chatbot. Well, how can I model this system that I'm interested in, or whatever. So what I've been thinking through is really need content that cuts through sort of the hype of new technology like this, and efficiently communicates fundamentals. I think the fundamentals that whole sort of history of research that is what provides these products. I think that's still important. And I think with geospatial data, that often means limitations. So, right, you're able to map out land surface change across the whole world. Well, what are the limitations involved there? And then I think some other maybe less specific things. So like allowing for flexibility with software packages to be able to keep up with rapidly changing technology, the importance of reproducible workflows that are transparent and maintainable, things like that. But yeah, talking about kind of the specificity of fundamentals in remote sensing, I still think this, like the limitations are very important. So like things like resolution trade-offs where we're still have limitations based on the time and the sharpness of images, as satellites can only be in one spot. So they have to choose, are we going to produce really high spatial resolution, or are we going to produce really high temporal resolution? And then one thing I care about, and was also kind of an excuse to bring in a video of a cat here, is the importance of ground truthing. So field work, I think is more important than ever if we're talking about these synthetic, AI produced things that claim to illuminate all kinds of different phenomenon on Earth. Yeah, I think it's really important to still go out and validate findings and the like. And so this is a video from some of my field work of a cat that this was an excuse to share. So I'll play it one more time. It was very cool, a little intimidating when we had to go out and measure like grass and plants and stuff down the road from there. But it's also to say that field work and ground truthing can be complicated and expensive as well, which is why it's nice to have the interplay between findings on the ground and geospatial data, like what I'm sharing here. But yeah, that's what I've been wrestling with. I'm sure folks here are probably wrestling with similar thoughts within the world of geospatial data and GIS and beyond. So yeah, I thought it may be interesting if we have time for discussion, if folks have similar thoughts, any additions to what I shared here, any questions about what I shared.
Yeah, we'll go ahead and open it up to everybody. And if you have questions or thoughts, please feel free to share. That was really awesome, Alex. Thank you.
Thanks.
Very, very fascinating.
Alex, where were you when you saw that cat?
That was in Botswana. Here, I can actually show on this map, actually kind of up like near where these zebras started, kind of up around right here.
I see.
Yeah.
Wow. And did you know that she was there, or did she just surprise y'all? She just walks by.
She kind of surprised us.
Oh
Because that
gosh.
grass is pretty long, so
Yeah, and she's kind of just hidden right in the top of it, right? Like
yeah.
she's just short enough. And then there's a fire image there. Was there also a fire in Botswana?
So that's a prescribed burn, and yeah, that is in Botswana. So that was a lot of my work, was studying like vegetation that's influenced by fire, and then these are savannas, which are like fire is a really important component of savanna ecosystems. And so right, there are a lot of prescribed burns going on. So that was another component of the research, was to be a part of prescribed burns and like measure different flame height temperatures and do kind of before and after like vegetation sampling and things like that.
Very cool.
Yeah.
Okay. Is there any other questions or comments from people? I'll give you a minute to, especially to chat, type in the chat if you need to. Awesome. Okay, well, Alex, thank you so much. We really appreciate that. It's fascinating, uh, fascinating amount of data. I'm curious to see where things continue to go.
Should be interesting.
Yeah. Okay, well, we will move on to our next presentation. This is going to be Josh, and he said he's doing a presentation on, can generative AI georeference maps? Sure, but how well? So Josh, if you want to take it away.
All right. Unmuted. Okay, and sharing my screen. Just minimize you guys. There we are. All right. Hello, everyone. My name, as many of you know, is Joshua Bin. I work right here at Baylor University Libraries, and I'm presenting today on can generative AI georeference maps? Sure, but how well? And boy, oh boy, I'm so glad I included that subtitle of But How Well. I will admit to you that the piling up of obstacles that needed to be solved in order to make this happen have been a great, great many. So instead of the original plan, where I was going to demonstrate an amazing and fully functional online tool, we're not doing that. Instead, I'm going to take you along on the journey that I went through uh, to really provide that intersection of two of my favorite research tools, artificial intelligence and GIS. Before we embark on this journey, I just want to ensure that that we're all in the same understanding of what we mean by terms like georeferencing or generative AI or local generative AI. So georeferencing is, as you will no doubt know if you attended Alex Martin's excellent webinar this past summer on georeferencing. Georeferencing is just connecting pixel coordinates on a scan map to real world coordinates so that it can then be overlaid on a map as accurately as possible. Generative AI generates text. That's what it does. By generating text in a structured chain of thought manner, which is what they do, it can reason by generating an internal text response to your prompt. It will respond to its own response and continue to keep responding to its own response until it reaches a point at which it will then provide the final response to your prompt. We all know about cloud AI models like ChatGPT, Copilot, Gemini, and many others. But to send large scale batches of map images to ChatGPT can potentially get quite costly because the chat interface is not really designed for that type of large scale image processing. Um, Instead, you want to use a cloud AI API to access ChatGPT, Gemini, Copilot, and all of those. But an alternative that is illustrated in this image here is using local AI, where instead of paying any fees to cloud AI models, you instead work with local open models, which can be entirely free so long as you have the GPUs to run them. That's right. This is the map. This is the sample map that I'm going to be using for today's presentation. This map is entitled Historical Markers of McLennan County, which is where Baylor and Waco are. So let's start with the foundational approach, or a base or default approach is to simply take a map. I'm going to use this example and go to a cloud AI and ask it to georeference it for us. This is what I did. So I'm going to go ahead and click this link, which is going to pull up a saved quick chat with ChatGPT in this example. I'll make this a little bit larger. All right, so of course I sent to ChatGPT the image, and then I sent it this prompt, right? This is your task. Georeference the map image and generate two distinct outputs. I want a KML and then a control point table if I want to also build this into ArcGIS. So then I'm specifying exactly what I need, the KML structure. The KML is the Google Earth file format. And so I'm specifying this is the format that I want. I'm giving it the example. And for the control point table, I'm specifying exactly what ArcGIS requires. If I were to load the image and of this control point table, ArcGIS would be able to instantly georeference it. And so I'm telling it these are exactly the columns that I need, and that's what ArcGIS requires. So it says, perfect, thanks for uploading the map. Let's proceed with georeferencing. It created the Google Earth file, which I'm going to open up in just a moment, right? It gives the text, so I can just copy it, paste it in a simple text file, save it as something.kml, And as long as it's in the same folder as a file called uploaded map.jpg, it will appear correctly, or it will appear where ChatGPT is intending it to appear. We'll decide if it's correct or not. But then, how brilliant is ChatGPT, right? It then is specifying that it's used downtown Waco, Baylor University, and Oakwood Cemetery uh, to as control points, and that it added a small rotation to align the historic maps grid. Here's the control table. And I didn't even ask it to do this, as you saw, but it tells me step by step how to do it. Then it even asks, would you like me to generate a world file for your JPEG, which would make it even easier to load into ArcGIS. Brilliant. So let's go ahead and let me go back to my PowerPoint because I added some reminders to myself. Here is where I'm going to go ahead and launch so that we can look and see exactly. So here is the ChatGPT KML file. If I were to open that in Notepad, it would look exactly like what ChatGPT had spit out. But with that prompt, sending it the image, we're about to get the fly through. It's Waco, at least. But the biggest tell for how off this may be is I-35. I-35 on Google Earth correctly goes from the Metroplex up north through Waco and then down to Austin. The georeferenced map has I-35 going almost crisscross. So it needed to be rotated a bit. Perhaps we can improve the prompt to get better results. I'm going to go ahead and close this and back to PowerPoint. But that local AI or working with an API is a much more effective way than, or my thinking was, is much more effective way than using a chatbot online like ChatGPT or any of the competitors. So now that not all of the big cloud AI models are fully, sorry, I take that back. All of them, 100% of the big cloud AI models are fully multimodal. That means that they can work across different modes of content, such as text, images, video, etc. However, most of the popular open models, meaning open, they are free to use and download, work only with text. So some of these most popular open large language models you may have heard in the news, DeepSeek made a really big splash last year. GPT OSS is OpenAI's. They took an earlier version of ChatGPT and made it open over the summer, so this is fairly new. Google's open line of their large language models, instead of Gemini for their Premiere, they have Gemma for their open version. Meta has the Llama line. Microsoft, instead of Copilot being their proprietary, Phi is the open version. And Quen is a really popular one that Alibaba out of Asia created. But they're not multimodal, meaning they only can work with text. If I'm going to use a local open AI model to help to georeference, maybe better than ChatGPT, it has to have vision capabilities. And I ended up using LLaVA, which stands for Large Language and Vision Assistant. And I went ahead and developed this, or I am developing this, there is no past tense, in Google Colab because my vision is to create an online public tool in Google Colab that anyone can access, but we're not there yet, as you'll see. So this is a screenshot of the notebook. It does exist, and if anyone wants to see how it, be able to get in the guts and take a look at what it's doing, definitely just let me know, send me an email, and we'll go ahead and make certain that this gets shared. All right. Now, so here is the initial idea. The code, the Google Colab code, will install Python libraries and allow the user to upload a scanned map image, then georeference the map, then output KML. But as we already saw, ChatGPT struggled. That was not a great georeferencing job. So how can we expect this much smaller and open model to be able to compete with that? The answer is obviously it can't. It won't. But a better answer than that is that it needs a lot of help and guidance. Unlike ChatGPT, where I just basically said, georeference this for me, we need to break everything down for a much smaller open model like Lava. So here's the basic workflow. Step one is to ask the Lava model to find identifiable locations on the map, and this model can do that through its vision capabilities. Step two is to go ahead and geocode those locations so that we have the real world coordinates, the Latin long. Step three is to obtain the pixel coordinates for these locations. Once you have the pixel coordinates and the real world coordinates, you can then georeference, output the KML, and it should be easy, right? I am sad to say that it is not easy. Here is the journey. Uh, let's chat through each of these obstacles and how they were resolved, just to give you an idea of what doing development with local AI like this can potentially look like. All right. So first, free geocoding options. We do not need AI to geocode. There are some really good and publicly available API services that we can leverage in the script to geocode. We don't have to bother a generative AI for that. I started off with the ArcGIS, freely available, limited amount per day, REST API. However, for non-paying customers, they do not support single address geocoding, but they require a bounding box in advance with the address to geocode, not suitable for this project. I instead ended up using Nominatum, which is a free public geocoder API directly from OpenStreetMap. Much simpler. Just pass it an address and it returns coordinates along with some accuracy data. There is a limit. They'll start to throttle you if you do more than a handful in a 1 or 2 minute period. But I built in a 1.5 second delay that seems to avoid any of that throttling in the script. The next issue that arose was insufficient spatial distribution of the control points. If the AI model, for example, concentrates all locations in a corner of the map, these errors are going to increase exponentially the further you move away from that corner. To force the AI to distribute the points, the script takes the map image and splits it into 4 quadrants. This is a screenshot from that Colab notebook. And like you see here, each quadrant is passed on its own with the exact same prompt, asking it to identify 2 locations from each quadrant. That really helped that particular issue. Next is inadequate identified locations. Some of the identified locations may not be the most ideal. Additionally, the first 3 points added when georeferencing are the priority to georeference, and subsequent locations are used more for fine-tuning or nudging the georeferencing. So the first 3 points would be the first order, and then all of the others would be secondary unless reject. Now, ideally, I'd love to have another AI model. Doesn't need multimodal to make these decisions, but for now, I employed what is referred to as a human in the middle approach, where the Colab notebook at this step then outputs exactly what you see here. It is organizing. This is the bottom left quadrant. It found 11th and 12th Street, 13th and 14th, 15th and 16th. those really are too close together, but that's another thing. And if you drop down, like in the screenshot shows, now the human can go in and specify this is a first order point, this is a non-first order, or I want you to reject this entirely. The next stop on this journey of discovery was a tendency of the model to concentrate on larger, more visible items that may cut across quadrants. So, for example, if a cemetery, a large one with big font, is halfway between one quadrant and another, it is very likely, and it was doing this more often than I would like, adding the exact same point to different quadrants. I wanted it to stop this. I couldn't stop it through the prompt. It kept doing it. So I came up with this guard band strategy. It adds a white band, a width of 20 pixels around the edges of all four quadrants before sending it to the local lava model in order to identify those points. And that cleared that up immediately, which was really nice. The next stop on this wild and crazy ride is handling geocoding outliers. There's a common algorithm in data sciences called RANSAC, or Random Sample Consensus. This is an algorithm that identifies georeference coordinates that do not line up with the other georeferencing points and removes them. So for example, if with every point except for this one, the map is in a good position, but this one control point is going to really skew that. The Ransack algorithm will remove that. And I must confess, I was able to import that from scikit-learn, and immediately it cleared up issues with outlier points. However, that's only if there's one or two outliers. If half of the points are garbage, Ransack is not going to solve that. The last thing, and this is the stop where I'm currently at. This is where I'm stuck at the moment, and I'm hoping there'll be no further issues, but this is where I'm stuck. So this is my present. After solving everything else so far, the lava model is being lazy, very, very lazy, and it is reporting the exact same pixel coordinate. The first pixel coordinate that it identifies for a location in a quadrant, it assigns the same coordinates to every location it identified in that quadrant. There's no reason for it. It's a smaller model. It's not a giant ChatGPT. It's being lazy. So that is where I am now. Let me go ahead, and this is my last bit here. I'm going to go ahead and run the lava KML. I use the exact same prompt that we saw with the ChatGPT with Gemini. It did much worse. For georeferencing, ChatGPT was much stronger than Gemini. All right, but this is the worst. However, well, let's see what we mean by worse. Here's that same to give us perspective. Here's I-35 in actuality. Now I-35 is going west to east in this georeference map. But that is not surprising because there are so many pixel coordinate errors due to the lava model's laziness, and that's where I am stuck right now. And so I'm going to go ahead and stop sharing because I think I went over my time, and I'll be here for questions unless our next presenter is here.
They are, but we'll go ahead and we have time for questions, so and comments. Oh, thanks, Jean Jolly. I see that. We appreciate you coming today. That's wonderful. And we do have the video, the recording going, so. Yeah. Josh, thank you so much. That was awesome. You really did a lot of work figuring quite a number of things out.
Trying. Couldn't get it. Couldn't get it. I really wanted for today, but at least I came up with the idea, you know what? I can just take you through the journey, even if the journey is not successful yet.
So that was pretty impressive. I really liked how you were showing us all the steps that you went through and how you problem solved. I think sometimes just learning how to problem solve is half the battle as well. So we learned a lot today. So thanks.
Thank you.
Josh, that was really cool. That is something that we've talked a little bit about trying to do here at UT Austin. We've probably had some conversations about some of our ideas over the years, and it definitely reminds me a bit of the workflow that we had developed here at UT Austin for trying to use machine learning to referencing. But this, I mean, we started all that work before LLMs became really popular, and so I think this is the way to try and do it now. Very cool. Feel very inspired after seeing your work here. Very impressive. And I am curious, which version of the lava model did you use? Which size of the model?
I was experimenting with two of them. I think I ended up with the 7B parameter size. That's the one I went with. There was a larger one. Was it 14 or 15? I forget what the larger, the
Yeah,
next
I'm looking
size
at it
up.
right now because I haven't heard of lava. And so yeah,
It was
there's
giving me
7,
bad
7
results.
billion, 13 billion,
It was
and
giving me
34.
worse results. So I just downgraded back to the 7.
Really interesting.
It was. In fact, Colab couldn't handle it. And so I shifted to a local computer
Yeah.
and was running it locally with a Python script instead of in Colab.
Yeah.
But I was not, I was disappointed by it. So I don't know. That was just my experience that the larger model was making more mistakes than the smaller one. So I just went right back to it.
Interesting. And was it quantized or was it the full?
No, definitely quantized.
Okay.
Yeah. These are very heavily quantized, maybe even 4-bit. Very, very right. They're a shadow of their real selves.
Yeah. This is really cool. I didn't even know you were doing this type of work. So yeah, I would definitely be interested in maybe talking to you more about this. Very cool.
Thanks, guys.
We'll open it up for any other comments or questions. Give a minute. If you need to type in chat, feel free to do so. Okay, well, thank you, Josh, again so much. That was awesome. Awesome, very, very much. We appreciated that. And we will now go to our last presenter. Sarah Lynn Fisher is going to be presenting on verifying and mapping location data and metadata for UNT libraries, digital collections. So thank you, Sarah, so much for being here with us. I know you were having to kind of come back from something else, so I appreciate it. And I will turn it over to you. We are recording, and then we will be stopping the recording at the end of our presentations, but we'll continue on with the game afterward. We just won't record that part. So take it away.
All right, thank you very much for having me today. I'm not sure if my presentation is in the realm of the technical work that others are doing, but I spent a lot of time looking at maps and looking things up on maps, so I thought you might be interested in hearing a little bit about that. Let me share my screen here. All right, is everyone seeing that? My slides? Okay.
Yes.
So I wanted to start first with an example of something that we digitized here in the UNT libraries that we are adding geographic information to, and it's not a map. It's a postcard of a hotel in the Lookout Mountain Hotel in Chattanooga, Tennessee. This was a postcard that was digitized from a large collection of items that we scanned for the Rosenberg Library. And this collection is in our digital repository called the Portal to Texas History. So this was an interesting example, I thought, because it shows all the different ways that we add, map, and verify location data for items in our digital collections. So you can see here that this is the user view of this item in the portal Texas history. On the lower right side of the screen, you can see that it says it's mapped, but also there's a pop-up that says recognize this place. If you can locate it, you can help improve our maps. So this is the user view of the geographical information for this postcard that was entered by the metadata creator in our we use a modified Dublin Core format that we call it UNT Libraries metadata format, but it is just modified from Dublin Core. In the coverage place name field, a couple of place names have been added. In Hamilton County, Tennessee. And this shows up for the user on a map. These maps, you can see the two below in the map locations, you can see the two blue, they're like a blue sort of square with a circle around it that is identifying the location of those two places that was entered in the coverage field. And these symbols on the map are showing up because they've been entered in our database that we have in our local system. We have a places database, and within that database, oh, before I get to the next slide, I'll say within that database, the coordinates for those places are entered, and then that gets mapped to for the user within the metadata view. But thinking about this specific place, some research is required. This is on the Lookout Mountain Hotel. I had to, figure out where this place was, and found a, Wikipedia page that had some coordinates, and also the coordinates in Wikidata are also a database that we use to verify location data for items in our digital collections. So we also use GeoNames database to verify, and this is when we're looking at places, because there's a lot of places that have similar names. And so this place that we identified as Lookout Mountain is identified as being in a specific county, which isn't the county that was previously listed in the record, and specific coordinates for that in GeoNames and also in the Wikidata item for that place. This is a screenshot view of our places database. So for each place that we have in UNTL, we can add all the administrative information about it, a feature class. We can put in a designation so that we have a lot of, because we have a historical items, there are historical places that were called something else previously or don't exist anymore. And that's always a challenge to find the coordinates and verify the locations of places like that. So we add a reference to geonames and Wikidata when those are present, and then also add in the coordinates. And we can add notes if, for example, the other day I was putting in the coordinates for a place that was a historical place. And so I used the Texas State Historical Association, their TSHA entry about that place, which said, well, it was 13 miles south of this. It had a post office from this date to this date. So I can put that information to kind of verify for anybody in the future who wants to know why the coordinates were entered that way. I can put that in the note field. So this allows us to distinguish the two places with the same name. And I chose this place for that particular reason, because there are these two places nearby each other that have the same name. And the one that we are referring to is actually the place in Georgia and not the one in Tennessee, which had been in the record previously. Something that happens that I deal with several times a week is when new items get added to our digital collections. Sometimes people add places to the coverage place name that aren't in our database. So then I have a list that shows up, well, of the list of all of these names that I then get to go in and investigate and add to our database. Some are easier than others because they follow standard formats, but recently we've been having a lot of conversations about places in Alaska that have changed the name of the census areas changed. And the boroughs in Alaska are just a challenge. And also places in Hawaii as well. And then how do we represent islands? For example, like you can see that Treasure Island is on this list, but that's actually within the city of San Francisco. And for our guidelines, the that we have set forth for how we're going to enter place names, the terminal name is going to be the name of the city, not an island. So, but some islands aren't within a city. So how do you handle those? So, and this is just United States. A colleague of mine is dealing with, spends a lot of time looking at places all over the world because we do, I like you. Your libraries probably have collections that mention places from all over the world, and countries change their minds about what they want to call places all the time. So, so it's never a dull day verifying place names. Oh, and I kept talking, here's more consideration. I talked about ghost towns. So just other verification methods, looking at historic maps. Um, if you know where the place name existed and you can find a map that was published during that time, maybe you can find uh, the the township and the range and kind of get a close approximate coordinate for that. So we do note in our database if we are approximating the location. If I go back, um, right below the designation, we can indicate that it's approximate and not, verified with an outside source. Within the metadata record, you can also identify a place name as historic. So, and then those places aren't necessarily on the map, but then you can add the place that it's called now to identify name changes. We we work with Oklahoma Historical Society, and something that's interesting, counties shifted, and so a town that used to be in another county and on that item is now in a different county. So that's where that's useful. Um, Places merged, and how do you treat a military base that is not where the names change over time? Also, a census designated place, is that, is there a population there? Um, is it considered a place? Those are questions that we deal with, and I'm sure you all have encountered in your time in libraries as well. I'll finish up here in just a minute. I'm also going through and verifying lots of places that we haven't been able to verify in Texas. Checking all the different sources and historic maps to figure out if these places are true places or they could be mistakes. And also we have coordinates that are suggested by users. So this is going back to the item that I talked about at the very beginning of this presentation, pretending that I was a user suggesting this exact place on the map here. So as we receive feedback, people will tell us, I know the place of where this photograph was taken. So then we can go in and improve the record and add a more specific location. And when that comes in via our feedback database, and there's a suggested place point added by a user, me. We can also add a place box that will show the coordinates of not just a specific place, but it was, you know, a map of these places, these with these boundaries as well. So then once the coordinates get added for that specific place, it shows up as the red circle with the white square in the middle, and that's identified as the precise coordinates of this place. Then we also have a special view where you can click on and see like items that are also, if they have some coordinates added, that they might be located near that other item that you're looking at. So I hope I didn't go over my time, and thanks everyone for listening today.
Thank you, Sarah. That was wonderful. No, don't even worry about time. We're doing okay. Great presentation. I like that it said Easter egg view. That was kind of cool at the end there. I will open it up to questions, comments, anything that people want to share. We're also looking in the chat. Susan mentioned how she says, I love how you geocode your digital collection resources. Really, really awesome to see the process. Yeah.
Yeah. Hi. Great. Love it. Love the website, the Portal of Texas History. Also, I was referring a patron to it the other day. So are you being reactive or proactive or both with the kind of checking locations? Are you responding to, I did notice help us map this, but I didn't do that. But that's my question. Thank you.
Yeah, so you're right, both. I mean, as someone is creating the record, if they know a specific location and can add the place point in the record at that time, it can happen there. But also, yes, we whenever we get emails, we have a central kind of database where all those emails go, and it shows up as a suggested place point, and then we'll go and verify that people know what they're talking about. Try to look at the street view on Google to make sure that if they took a picture of a place that it seems reasonably correct. And then we can go back and edit the record to add the place point. Yeah, so it's kind of fun to do that for things that aren't maps, Specifically photographs, like we have an example I like to use is we have a mall here in Denton, and there's a picture, you can get the precise coordinates of like the exact intersection where that photograph was taken instead of just the mapping that, if you identify our town, it's just the city center and not the place where that photo is. So.
Yeah, it's funny you asked that because it's a question from a researcher far away about Austin, and that you all have the Austin History Center photographs. And so I was trying to decide what part of 6th Street, looking at the old state capitol, with a streetcar it was, and it was kind of fun, but it would be great to get people that have, know better to in there. Thank you. So cool.
And we do have a question in the chat. What software are you using on the website DIMS interface to display the mapped coordinates?
Yes, I wrote that down. No, I know I just wrote this down recently. That's not my area, but I know that I asked this question. So I will get back to you in just a minute.
That's
I don't know if this is conclusive. Maybe Alex or Michael can confirm, but I did see on the maps, it did say Esri in so I wonder if it's ArcGIS Online that is being used to display the maps, if that's what the question is asking.
A follow-up is, in other words, what's converting the latitude longitude to the interactive map?
Yes, I know what you're talking about, but the name of it, yes.
And I hadn't seen that, Esri, so it's good to know that you.
I will, let me check, and if I can get back to you before the end of the hour,
Yeah.
I will.
For sure. I think, let me go to my notes here. We have this down actually as 3 to 4:30, and I want to be respectful of everyone's time. We do have a a little trivia thing we had prepared that was cats related, but it definitely had a lot more geography GIS stuff related in it. A little more technical. I was not able to answer most of them, but we may just save that for our December meeting. If everyone is okay with that, looks like it. Yeah, so this is an encouragement to come to the December larger group meeting. For those who are watching the video, we won't be having that today for the trivia, but that's okay. And Sarah, if you want, you can also share the answer with me, and then I can share that out with the GIS group so that they can see the answer to that question. And I will go ahead and make a copy of this transcript. I'll save the chat so that way we can get back to answering that for everybody. So that's not a problem at all. Yeah.
Yeah,
Okay, go ahead.
this is
Josh.
a pattern now.
It is. I think we missed the activity last time too. Oh, here we go. We've got it in the chat. Leaflet.
Leaflet, yes. Sorry.
Okay,
Took me a minute.
great. No, thank you so much for looking for that. That is wonderful. I'm so glad we can go
Even
ahead and answer
better.
it.
Then you're using complete open source.
Yeah.
And
Kara,
then we have one more
yeah,
chat.
we will be changing. I'm going to just speak for Alex on this one. We will be changing the meeting dates. We had a question, I think it was from Susan, in the email about how we had a meeting scheduled for November after, like, right after Thanksgiving. It was like, no, we're not going to be having that meeting. So I think what we'll end up doing is changing both those meetings and putting them to an earlier time in December.
Yeah.
So November, we usually use this pre-GIS day, and so we don't worry anything more after this in November. And then in December, we could just go a week early or something. But for us to do it, it just sets it for the whole year is why that ends up landing on your calendar that way. So
Yeah.
good
Very
eyes,
true.
guys. Thanks for
Yep.
checking.
I'm going to go ahead and stop the recording.